Okay, so mathematical induction is a method of proving these conjectures true. And so I'm not gonna go over the hard, like what you have to write. We'll deal with that when we start uh, with the test. But I just want to give you the basic layout of mathematical induction. So you can't with a conjecture. And so you were told to prove, so mathematical induction. And so you said like prove that 1 plus 2 plus 3 up to n is equal to n over 2 times 1 plus 2. Or maybe it might be, maybe it was written in the book as like n times n plus 1 over 2. And you knew this from series of z-quests. And the idea is for n, all positive integers. Okay, step 1, show it works for the first one. So the first positive integer is 1. So show that the statement for 1 is true. Because maybe if it's not true, I mean, you can come up with conjecture. You might think that you have something, but it just might not be true. So let's test it out. So for 1, it'll be 1. So for P1, 1 over 2 times 1 plus 1, which is equal to 1. Nice, it works. Personally, I like to try like 2 or 3. That's just my style. But you don't have to. So for P of 2, it's like 1 plus 1. So it's equal to, and which we know is 3. But the formula says it's 2 times 2 plus 1 over 2, which is 3. And you can see it's going to work. So it's good. You also know it's good. And IB's not going to ask you something that's not true. Here's step 2. Assume it works for some n equals k. Assume P, where n equals some k, is true. What you then have to prove is that the k plus, given this, prove that k plus n equals k plus 1 is true. Prove that P equals k plus 1 is true. And this is a logic statement. This has to do with logic, which they don't teach anymore. The idea is, this is known as proof by assumption. So we're going to assume that the hypothesis is true, and we're going to take that information, hope that each mathematical statement that we follow through ends up with a true statement. Okay, now, where have you seen this before? Here, watch. So let A equal B, right? And then multiply both sides by A, right? So assume this is true. This is true, and we're following through. Now let's subtract B squared from both sides. Now we're going to factor. Well, the next step is we divide both sides by AB. We have A plus B equals B. Well, because this is equal, we have 2B equals B and 2 equals 1. What's the problem? I want you to think about what's the problem with this proof? What happened? Well, anyone sick? Well, the error was right here. This was false. You can't divide. If A equals B, then A minus B is 0. And so this false, because we threw something false in there, we end up with a false conclusion. So this is the idea behind mathematical induction. We're going to assume that some k is true and prove that the next term is true. So if P of n equals k is true, that means that 1 plus 2 plus 3 up to k is equal to what we think it should be. We're going to use this, and hopefully we need to prove that 1 plus 2 plus 3 plus k plus 1 is equal to k plus 1 times k plus 2 over 2. That's the idea. So once again, step 1, step 2, Step 3. Okay. This is our assumption. We're assuming that this is true. We need to prove this. How do we deal with this? Nice. What you're going to do is you're going to manipulate the left side to look like the right side. So I'm going to look at my left side, and I have 1 plus 2 plus 3 plus k. Well, the assumption was that this equals k times k plus 1 over 2. And I'm going to add that to k plus 1. Fine. Next, if I'm going to add fractions, I'm going to have to multiply this top and the bottom by 2. Fine. Next, I'm going to factor out a k plus 1, leaving me with a k plus 2 over 2. And I've just proven because I made the left side look like the right side by using my assumption. My conjecture is a theory according to math laws. And so that is how we proved that the sum of an arithmetic series is n times n plus 1 over 2. Let's try another one. The claim is that the sum of the first n odd numbers is equal to n squared. What was the condition? That n is a positive integer. Okay, let's think about that. Well, we kind of proved it. You kind of proved it. So we know that the first one works. 1 equals 1 squared. Let's try. We tried a couple of them. 1 plus 3 equals 4, which is 2 squared. Good, and you can do 3 if you want. You only need to do 1. So we have the first. So we know that 1 works. Now we want to make the first statement. So we're going to show that P of n equals k is true. Now we looked on the sheet. What is the first term? It's 1 plus 3 plus 5. What is the kth odd term? The kth odd term is 2k minus 1, right? Because the first one is 2 times 1 minus 1. The second term is 2 times 2 minus 1. The third term is 2 times 3 minus 1. So the kth term, we're saying this equals k squared. The kth term is 2k minus 1. That was why I went over the sheet with you. So we're going to assume this is true. So we need to look at the n plus 1, a k plus 1 term. So first of all, what is the series? It's 1 plus 3 plus 5 plus 2k plus 1. This is the kth odd term. What is the next odd term? What is the k plus 1th odd term? Okay, 2k plus 1. And we need to prove that the sequence is equal to k plus 1 squared. Good. Okay, I'm going to erase this out of here. Let's get to work. Here. So based on the assumption, and this is how all these work, based on the assumption, the first part of the left, this whole part, this is equal to k squared. Well, k squared plus 2k plus 1 is equal to k plus 1 squared, and we've actually just proven, according to the math rules, that the sum of the first n odd numbers is n squared. This is based on how we do things in math. So this is how we prove conjectures. Prove it's true for the first one, assume that it works for some kth term, and then prove it works for the next one. If you think about it, you've covered every single term. Because if you proved it for 8, then it proves for 9. But then if you proved it 9, then it goes to 10. So this proves it for infinity. Okay, and that's the idea. Okay, well let's move away from these type of conjectures, and let's move to disability rules. You have to practice these. There's not that many. They might show up. And we'll go through it in the year. but I just want you to have, I want you to have seen it. Okay, let's try the next one. The next, it's a divisibility rule, and it's a prove, let's see, where is it? Prove, let's see, prove that 6 to the n minus 1 is divisible by 5. Now, there's a couple of ways to do this. You might see it different ways. Let's see. First of all, is this true? Well, I'm sorry, and then the condition for n is, n, once again, is a positive integer. Because 0 doesn't work. So they're very clear on where they want you to store it. You're like, fine. So for p of 1, 6 to the 1 minus 1 equals 5. That's divisible by 5. And you can test it out. Once again, I test it out. 36 minus 1 is 35. Works. 6 to the third is 2 16s. 2 16 minus 1 is 2 15. That's divisible by 5. So that works. Okay, that's step 1. Step 2, assume that 6n minus 1, well, on the sheet I told you how to express when something's divisible by 5. It's equal to 5m, right? And so, I'm sorry, we're supposed to write, assume that n equals k, so 6 to the k minus 1 equals 5m. We have to prove that p equals n equals k plus 1 is divisible by 5. So we have to show, you have to show that 6 to the k plus 1 minus 1 is equal to 5 something else. Because obviously it's not going to be the same divisible, but it's still 5 times something. Okay, what's going on here? Well, we assume this to be true. We assume that this to be true. So we're going to take this and stick it in here. But we first have to do a little manipulation. So the first thing we're going to do is, let's see, what do you think? Well, let's pull the 6 out of there. Now, the easy way is to look at that statement up there and go, oh, you know what? 6k is equal to 5m plus 1, right? Minus 1. And then we just manipulate this. What do we have here? 30m plus 6 minus 1, 30m plus 5, and this is 5 times 6m plus 1. Therefore, and let this be equal to n, and what we've done is we've manipulated this to show that 6 to the k plus 1 minus 1 is actually a multiple of 5. The n ended up being 6m plus 1, but that's besides the point. What's another method you can use? This is a little old school. Sorry. Another method 2. You pull out the 6, so let's go over here. Method 2, pull out the 6k minus 1. Rewrite that 6 as 5 plus 1. So to the 6k minus 1. So you have 5 times 6 to the k plus 6 to the k minus 1. While, if you think about it, this is a multiple of 5. 6k minus 1, this is already 5m. And therefore, like over there, you have 5, 6 to the k plus 1, and that's sufficient to show that n equals k plus 1 is also divisible by 5. So once again, once you practice this, you'll get this down. The idea is prove it's true for the first term in the not the domain, but like the valid like numbers. Assume it's true for n equals k, and then use that to prove that n equals k plus 1 is true. Shall we try another one? Another divisibility one? This one's a little trickier, but well, let me find. Okay, let's take a look at this problem. Prove that 13 to the n minus 6 to the n is divisible by 7 for all n greater than or equal to 1, or a positive integer. So for step 1, test out the first term. 13 to the 1 minus 36 to the 1 equals 7. That's good. You can do, let's see if this works for 2. Let's see, 13 squared minus 6 squared, that's 169 minus 36 is equal to 133. Is that divisible by 7? Yes. 1, 6, 19. Nice. So that worked. That's kind of interesting. So let's go through step 2. Let's see. Assume that P of n equals k is true. That means we mean to say that 13 to the k minus 6 to the k is equal to 7m. Next step, we have to prove that 13 to the k plus 1 minus 6 to the k plus 1 is equal to 7n. Well, let's take a look at what's going on here. Well, there's a little trick to the trade. First of all, pull out the 6. First, pull out the constant. So it's 13 times 13 to the k minus 6 times 6 to the k. Okay. What do you think? Well, the easier trick is to manipulate this. So you say 13k. The easier trick is take this statement and say, you know what? 13k is equal to 7n minus plus 6 to the k. So we can substitute that in there because we assumed it was true. So we're allowed to use it. Let's see what it does for us. We have 13 times 7m plus 6 to the k. And then what do we have here? Minus 6 times 6 to the k. Let's distribute the 13 through. We have 13 times 7m plus 13 times 6 to the k minus 6 to the 6 to the k. Well, this works out pretty nicely because we have 7 times 13n plus 7 times 6 to the k. And if both of these are divisible by 7, the whole thing is divisible by 7. And this is our n. This is our n. Nice. Another so that's what you can do. Another technique, the way I used to do it, I guess maybe I'm changing it, is at this step, just rewrite 13 as 6 plus 7. 13 to the k minus 6 times 6 to the k. And then you see that, that works out nicely. Yeah, because you have 6 times 13 to the k minus 6 times 6 to the k plus 7 times 13 to the k. If you factor out the 6 here and you're left with 13k minus 6 to the k plus 7 times 13k, you notice that this whole thing, based on the assumption, is equal to 7m. And we have both of these. We have 6m plus 13 to the k, or 7n. That's the idea. So these are the two manipulations. Actually, I'm kind of liking this way better now. Okay, those are the two divisibility. Is there another one I would like to do? Prove that n factorial is greater than 3 to the n for n greater than or equal to 7. Looks weird, but you're going to be told mathematical induction. So you can get most of the points by just following the steps. First of all, what's the first term n we're looking at? We're looking at n is greater than or equal to 7. We're not starting at 1 or 2. We're starting at 7. Pay attention. So, for step 1, p equals 7. Let's see, 7 factorial, is greater than 3 to the 7th power. Obviously, this would be a calculator question, Do I have, yeah, this is, it turns out that 5040 is greater than 2187. For my own personal edification, I tested at 6. This would not be a part 1. If this were a part 2, obviously it would be part 2. Just to test it out, 6 factorial equals 720, and 3 to the 6 is equal to 729. So that's why it doesn't work. But after 7, it kind of like takes off. And if you think about this, is kind of like comparing functions. So exponentials versus factorial functions. So let's see. So we showed that this is good. It's true. Okay. So P, this is true. Now, next, assume that P equals N equals K is true, right? So the statement is that the statement is that K factorial is greater than 3 to the K. We're assuming that's true. Now we have to prove that P equals K, the proposition that N equals K plus 1 is true. We have to prove this. So we have to prove that K plus 1 factorial is greater than 3 to the K plus 1. Let's see. What do you think? Well, let's work with the left-hand side. What is K plus 1 factorial? Well, we know that's equal to K plus 1 times K factorial. Well, what do we know about this? Well, we know that it's greater than What do you think? Well, what do we know about K plus 1? What do we know about K plus 1? Well, where did we say K started at? It starts at 7, so, and what do we kind of know we want? I mean, you could write, we know we need to be greater than 3 to the K plus 1. And so you might work backwards. You might say, well, I know that's greater than, that's equal to, it's equal to 3 times 3 to the K, because you're going to be using this. But how do you know that this is greater than that? Well, here's the logic that you have to think about. Here's the logic. So you're going to say, because K is greater than or equal to 7, K plus 1 is greater than 3. That means this statement is greater than 3 times K, which is greater than 3 to the 3K, which is equal to 3 to the K plus 1. It looks a little weird, but that's the idea. So let's go over this again. We needed to prove that K plus 1 factorial is greater than 3 to the K plus 1. We knew that K plus 1 factorial is equal to K plus 1 to the K factorial. We broke this down because we knew we needed this statement. We were going to use it. We also knew we needed to be greater than 3 times. Because we knew that K factorial was going to be replaced with 3 to the K, and we knew we needed to get 3 to the K plus 1, we knew we needed a 3 in here. And that's the logic. You know that K plus 1 is greater than 3. So K plus 1 K factorial is greater than 3 times K factorial, which is greater than 3 times 3 to the K, which equals 3 to the K plus 1. Therefore, we just proved it, and then we just proved it. That's the whole thing. It's a little weird, but we'll just practice it a couple of times in class. The last thing, actually, I don't know. Just do the problems in the book. We'll go through it. Nice. And this works. This is for all subjects. This is for series and sequence. This is for trig, and this is for calculus, and this is for probability. So it's a lot of work.